Let's start. So we will start with the next part of the first chapter, that is electric potential. Electric potential and capacitance. So what are all this? What is electric potential? Before we understand the concept of potential, potential is a different concept. So in the last chapter we have learned electric field. In this chapter we have learned two things. If you look properly, we have done three new phenomena we have learned in electric first chapter. You have learned force, you have learned electric field, and then you have learned flux. These three things you have learned. You have learned two vectors and one scalar quantity. Now what is the use of now? If I summarize this thing, you can see that whenever charge comes in existence, there is force also come. This force we call it as a Coulomb force, and it is a central force, also square law force, inverse square law force. So this force, and whenever this force is present, along with there is an electric field is present. This electric field we cannot visualize, but it is present there. We can only see its effect. So in order to understand this electric field, we have mathematically defined electric field lines and so on. Now when electric field lines is present, electric field decide some properties in a region for charges. So in order to know further about these properties, we need to know what is this flux. We need to know how strong is an electric field in a region, how much dense is it in a particular region, how dense is it. So that is highlighted by this phenomenon called electric flux. So now we will proceed now further. Now you will notice one thing. Before I carry on, try to visualize with me here something called electric potential. Before I come to electric potential, you have to keep one concept, one picture in your mind, which I am going to explain you now. Imagine that this is a north pole of a bar magnet. This is a north pole of another bar magnet. Now you can think, how come this is an electric chapter and I am explaining you with this bar magnet? Why? Now if you see, they are separated by a distance r, these two north pole. Now if I ask you that you bring this keep this one fixed, and you try to bring this one as close as possible. Try to bring this one close. Will it be, if it is quite difficult to bring, because they are going to repel each other. Now by difficulty, you see I have used the word difficult. So that means if you are quite strong enough, you can force it. If you are weak enough, if you are quite weak, you won't be able to bring it up to, you may have to push this north pole up to this point A. Beyond point A you won't be able to move, because you are weak, or your capability is less, or your potential is less, right? Similarly, if you are strong, you may push the magnet against the repulsive force between two north poles, and you may bring it up to this far. That means your potential is more, your capability is more, right? So this is the concept of potential or capability. So why not the same thing for charges? Why not the same thing for charges? If I take 2 plus q charge, one charge plus, another one also plus. Now if you try to bring one charge q1, another charge q2, if you try to bring q2 close to q1, definitely you will have to perform some work. You will have to do some work. And if this charge is more, if q2 is more, repulsion will be even more. Imagine this is fixed, and if this is 2 coulomb, you have to do work, more work. And if it is 4 coulomb, you have to do even more work, and you have to be even more strong to push it towards q1. So can you understand one thing, that this is a concept of something which you cannot see, which has no direction, but it is something which exists, which you can only feel it, which we can, when you perform it, you do. Such thing is called electric potential. So what is electric potential? Electric potential is actually it is defined as how much work are you going to perform to take a unit charge. Okay, that is called electric potential. At any point P, we will see that what is it. So this is the concept of electric potential. I'll give you another example from classical mechanics. Let's say this is a two person. This is a one very thin person, and this is a very strong person. And here is a stair. I keep a bucket of water. I keep it a bucket of water. Out of A and B, who do you think, for whom do you think, whose potential is more to take this bucket of water to this height H? Who will be able to perform more? Whose potential will be more? Whose capability will be more? Definitely B, right? So we are talking about some potential, some concept like this. So how much work are you going to perform to bring a unit test charge? We're going to see that. So electric potential. So what is electric potential then? So electric potential is nothing but is mathematically explained as the work done. It is the work done per unit charge. That is V equals to W by Q naught. Work done per unit charge. From what? I will come to that. Don't worry. This is just the very basic definition and most fundamental definition of potential. This is not what we are going to do. We are going to define it even further. Just keep following. So, but this is the main equation of electric potential. So electric potential is defined as the work done per unit charge to bring a charge from somewhere and place it in the electric field of another one. Okay, so that is the electric potential. What do you think its SI unit is, or SI unit or dimension is? So V equals to, we know, W by Q naught. So its dimension will be what? So dimension will be, we know, V equals to, this is energy, mL square T to the power minus 2, and this is ampere T. Right? So then dimension must be equals to mL square T to the power minus 3 ampere inverse. So this is the dimension of electric potential. SI unit would be volt. Okay? So this is electric potential, but this definition is incomplete. To understand electric potential, consider another situation. So electric potential at a point. Let us see this. Then we will find out electric potential. So let us see electric potential. How else can you define it? Electric potential at a point. So let's say I have a plus Q charge here. This is I placed at the origin, and in its electric field, I will not show it with the help of any line. I will show this is the point P, because electric potential is a scalar quantity. It is not a vector quantity. Okay? So electric potential, you can see this is at a distance, let's say certain distance R from Q, and you are bringing a charge Q naught from infinity, very very far. So more close you come, what will you have to do? You will have to do some work. right or not? Correct? So this work done will get what? Stored as this work done per unit charge will be known as the electric potential at a particular point. So let us see this. So let us consider a charge Q plus Q placed at origin and another charge Q0 is brought from infinity to a point P on the electric field of plus Q. Okay, the point P is at distance r from Q. Now how can we find it? So you can see, we can write this as so you see, in order to bring this, what will you do? You will be gradually taking the charges, because by every one unit distance you move, you feel the repulsion, right? More close you go, you can still feel the repulsive force more and more and more and more. So more close you come towards plus Q, you start feeling more and more, right? Now I will show you like this. Let's say this is the point where currently Q is, and you make a displacement of dx, and this point is at a distance of x from Q. Now if dw or dx is the small displacement, small distance moved against the direction of against the electric field of plus Q. So where is the electric field direction? Electric field of plus Q is this side, and you are coming from right to left. Okay, then can I write, so what will be the potential then? So we know V equals to work done per unit charge, and this can be written as what? Force into displacement dx by q naught. So that means dV is equal to f dx by q naught. Now for total potential at particular point P, so we are bringing from where to where? You are bringing from infinity to P. So potential V will be then how much? I can write this as, you are bringing the charge from infinity and you are placing it at a distance r. So this would be f dx by q naught. So f is, what do I know? Coulomb's law says infinity to r, then this should be q naught by r square into 1 by q naught dx. So q naught get cancelled. What do I get here? And sorry, not r square, it would be x square. Why x square? How far is the force? This is at a distance of x. So I get here, so I'm going to get here V equal to infinity to r k q, I'll take it out, I'll be left with 1 by x square dx. So V equal to kq Integration of 1 by x square dx, if you remember, I have taught you, it is x to the power minus 2 plus 1 by minus 2 plus 1. So that gives me how much? Minus 1 by x, infinity to what? Right? You are bringing from infinity and you are placing to where? R. So then I can write this as kq, then minus 1 by, wait a minute, here one thing is there, you see his minus is coming. How come his minus is coming? I'm going to explain that to you. For right now, let us do it by minus only. 1 by r, then minus 1 by infinity. Let it be. But wait a minute. Come to this direction, come to this one. So, electrostatic force of repulsion is which side? At this point P, the force of repulsion is this way. Hold on a minute, please. हेलो
हेलो
हेलो हाँ बोलिए
दादा आज की गाड़ी বার করবেন নাকি
না না
ঠিক আছে
হ্যাঁ হ্যাঁ ঠিক আছে
আমার গাড়ি পিছনে আছে না লাগি
না না আজকে বার করবো না আজকে বার করবো না আজকে এখনো তো কোনো প্ল্যান নেই কিন্তু এমার্জেন্সি এসে গেলে কিছু বলতে পারছি না কিন্তু বেরোনোর কোনো এখন নেই
আমাকে ফোন করলে হবে
হ্যাঁ 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 ঠিক আছে Okay. Sorry, I just received a. So you see, look at the diagram now. So electrostatic force, there is a force of repulsion to Q naught is actually this side, and you are bringing the force. The displacement x is this side. What is the angle between them? Is it 180 degree? So if it is 180 degree, that means there should be a minus sign here, right? There should be a minus sign. So I hope you understand from where this minus sign is coming, because force and displacement, they are in opposite direction. Although you are applying the force, but your force is the force which you apply. Please make these things clear, very clearly here, that at this point where the charge Q naught is there is a repulsive force, which is the Coulomb force Fe, and there is an action force which you are giving to bring it. But this comes into play when this is present. If this is not present, there is no question of Fa. Understand? So all the time we are going to be looking into this force, not this. Okay? We are going to pay attention to this, and based on that we are going to classify, is it a positive potential or is it a negative potential, based on this. So I will give you an example of, so let us see this now. So that means this one should be a minus sign, this one should be a minus sign, here also a minus sign. That means I get here V equals to what? V is coming to be K Q by R, or V equals to 1 by 4 pi epsilon naught Q by R. This is the electric potential where? This is the electric potential at P. This is the electric potential at P. Similarly, potential difference between 2 points also we can find out. So let me give an example of this. Now imagine this was a negative charge. Imagine I took a positive charge. If this was a negative charge, then what would have happened? So I'm just giving you briefly here. Imagine that here is the negative charge. Here is a negative charge, and you are bringing the Q naught charge from infinity towards A. A is the distance of R. So more close you come, now what will happen? Minus Q is attracting Q naught. Come to me like that. But you have to prevent it. So if this is at this point, the force of attraction is this side, that is Fe is this side, and you are applying the forces this way. Correct? And which way are you bringing? You are bringing in the same direction. Your displacement AC is also in the same direction. So in that time, work done would be how much? dW will be how much? F dot dx is equal to F dx cos 0 degree. So that means V will be that time how much? V will be positive or negative? You tell. You decide now. I'm doing it. So K integration you bring from where to where? You bring it from infinity to R. Q naught by Q naught into 1 by x square dx. Right? This is the point we generally take. This as dx, and this is the point as x. Small integration. First continuous integration this is. So then Q naught get cancelled. KQ is out. Integration from infinity to R. So 1 by x square dx. That gives me KQ minus 1 by x infinity to R. So that gives me KQ minus 1 by R minus 1 by infinity. So V is what? Minus KQ by R, which is nothing but 1 by 4 pi epsilon naught minus Q by R. So this is negative potential. So this is plus potential, this is negative potential. Pay attention, we are interested in this force and not on the force which you are applying, because your force which you are going to apply is the reaction force, is not the action force. The action force is Fe. Every action has an equal and opposite reaction. So I hope you have got the picture. So this is the electric potential at a point. Understand? And look closely, note, very important thing to highlight here. Let me clean the board now. Let me clean the board. So we can see that V is inversely proportional to R for a single point charge. I will teach you that later. I'm going to show you that for dipole it depends on square, and if for quadrupole it depends for a cube. We'll see that. So now that means, how is the potential? I'll come to that after a while. The graph between potential and all will come to that. For now, so based on the above concept, electric potential can also be defined as electric potential at a point can also be defined as the work done to bring an unit charge from infinity to a point on the electric field. Electric potential point can also define electric point. Actually, I should have written like this: electric potential at a point on the electric field of another charge. Okay, is point from infinity to a point on the electric field of a charge plus Q. Okay, So this is electric potential. So that means it is the work done. So I'm talking about this. It is work done to bring a charge from infinity and place it at a point P. Place it at a point P in the electric field of a plus Q charge. So you can see Q naught is a unit charge. So we see that to bring something there, what is the capacity you need to bring a charge from infinity, and why infinity? Because at infinity we consider the electric potential to be 0. Okay, why infinity? So we have to go for very very far where V is almost 0. There is no effect of any other charge potential is present there. That's why infinity. Okay, so then similarly we can explain electric potential difference. Electric potential difference between 2 points. Difference between 2 points. So if I consider 2 points, not necessary this has to be a charge only. Later on in current electricity, all this concept will be translated to a circuit. So imagine this is a plus Q and this is point A, this is point B. So electric potential difference between A and B, which one do you think is at higher potential? Is A at higher potential or is B at higher potential? And how can you answer this? Which is at higher potential? Definitely VA is greater than VB. How I am saying? I am using this relation. Is inversely proportional to R. Here R1 and this is R2. R1 R2, right? So R1 and R2, definitely R1 is greater than, as R1 is greater than R2, correct? So electric potential at a point will be, it is the potential difference we need to find. That means what is the potential difference between these two? Between A and B, what is delta V? This is what I need to find, correct? So how to do it? Let us do this now in our next derivation. Clear? So electric potential difference between 2 points, in an electric field, of a charge. So our same old diagram. So this is plus Q, this is A, this is B. Clear? So now we need to find the electric potential difference between these 2 points. So how to do it? We can easily do it. So we can define like this way, that the electric potential difference between 2 points. So given that this distance is R1 and this distance is R2, between 2 points is defined as the work done, as the difference in work done, as the difference in work done to bring a charge from B to A. So that means we can define like this. So VAB will be, how can I write this? So can I write, it would be actually work done to bring a test charge from infinity to A by Q naught minus work done to bring a test charge from B to Q naught. You can explain this also. You can give this definition also. That the electric potential between any 2 point A and B is defined as the work done to bring a test charge from infinity to A minus the work done to bring a test charge from infinity to B. Correct? So then this can be written as what? I can take 1 by Q naught common out. What is left here? It will be left with W infinity to A minus W infinity to B. Correct? So this thing can be written as now 1 by Q naught. This would be force into displacement. Correct? Force into displacement. Correct? So the displacement, how you can write it? You can write this would be a force into dx1 dx2, like that way we can do it. Or can I write this as this is the delta change now? So let us do like this. So instead of doing like this way, I can write it is 1 by Q naught delta or W AB by Q naught. What is the work? That means it is between these two only, na? This is the W change in work done. Correct? So this work done, so sorry, Q naught I have already taken. So then for small work done dW, for small displacement dx, it will be what? VAB will be 1 by Q naught F dx cos of 180 by cos of 180. So then it would be, now we need to integrate it to get the complete work done. So V would be equals to, but you are bringing from where to where? You are bringing from infinity to R1 and infinity to, that is, this is between R2 and R1, right? B to A. So it should be R2 to R1. Okay? And 1 by Q naught is there. So K, Q naught by X square. Same derivation only we are changing the limit, nothing else. So I get here K R1 to R2, sorry, R2 to R1, then Q also you take it out, 1 by X square dx. Sorry, there should be one minus because this cos 180. So 180 is minus sign should be there. Then I get here V equal to minus KQ, integration of this one gives minus 1 by X. Now this time my limit is from R2 to R1. So that gives me KQ 1 by R1 minus 1 by R2. So V is 1 by 4 pi epsilon naught Q, then, sorry, I should write like this way, Q by 4 pi epsilon naught 1 by RA minus 1 by RB. So I am specifying you that this is RA minus RB. Why? VA minus, so this you can write like this also, no? VA minus VB, because this is actually Q by 4 pi epsilon naught 1 by RA minus 1 by 4 pi epsilon naught Q by RB. Definitely I told you VA is greater than VB. So this is our potential difference, VA minus VB. I hope you understood this one. So every time this is a different way to approach to it. This time I did it in a different way. This is a simple way I've done it. It can be done in another way around also, using electric field also. That way also can be done. So now let me clear this, give you the sense of electric potential. What is it all about? So let me give you a question. Let's start with an easy question so that we can understand it. So I give you a 2 microcoulomb charge here and I ask you, what is the electric potential at P, whose coordinate is 10, 0 centimeter. So how will you find it? Very simple. So find V. Find V, P. How will you find? So V would be equals to 1 by 4 pi epsilon naught 2 into 10 to the power minus 6 divided by 10 centimeters. So 10 into 10 to the power minus 2. So this gives me 9 into 10 to the power 9 into 2 into 10 to the power minus 6 divided by 10 into 10 to the power minus 2. So this and this get cancelled. I get here minus 4 and 9 2 is 8 to 2 5. So that is 9 by 5 into 10 to the power 9 minus 4, that is 10 to the power minus 10 to the power 5 volt, right? And 9 divided by 5 would be 5 1 and 4, I think 5 1.8 into 10 to the power 5 volt. So that is the potential at P. Okay, that is the potential at P. Now let us see what is the potential difference between 2 points. Now look at this case. Now I told you not necessarily it has to be always a plus charge. Always has to be a charge. I give you a certain distance like this. This is okay. Now let us keep it to charge only. 10 microcoulomb. This point is A. This is at a distance of 5 centimeter, and I am considering another point B, which is at a distance of 10 centimeter. So what is the potential difference? Find VAB. So find VAB. So VAB, how will you find? So it's very simple to find. So VAB would be VA minus VB. Correct? So how can I find? I can find this as K Q 1 by 5 centimeter, 5 minus 1 by 10. I'll change it later. So then KQ 9 into 10 to the power 9 into 10 into 10 to the power minus 6. And if I take the LCM of this thing, I think 10 is the LCM. So 5 2, 10 minus 1, 1 only. So 2 minus 1 is 1 by 10. So 1 by 10 into 10 to the power minus 2. So this one again gone. That gives me minus 4, 10, 10 cancel. So I think we're left with 9 into 10 to the power, 9 minus 4 is 5 volt. So VAB is this much volt. Okay. So I think I will stop today this much only. Any doubt? Any doubt regarding today's class?
No, sir.
Okay, then I will.
No, sir.
Okay, then I will get into more important topic next class.